All right, good morning, everyone. Welcome to the SOFIA Proposal Tools webinar for Cycle 9. Today we will be talking about what is new for Cycle 9, as well as providing some examples for each instrument to help build strong proposals. So first up, we have Ariel Mouillet, who will be talking about Cycle 9 specifically. And also just a note, this webinar is being recorded. So Ariel, the floor is yours. I will give you a warning when you have 10 minutes.
Okay, thank you. Thank you, Cassandra. I'm Ariel Mouillet. I'm a scientist at the SOFIA Science Center. I'm really happy to see many people online for this webinar on how to propose for a Cycle 9 proposal. A few things you may have received if you were on the e-newsletter, the fact that there is a Google Doc where we can ask questions, but otherwise question you can ask them through the chat window in WebEx, and we could either respond to them right away or at the end of each talk. So I'm going to share my screen just with the schedule for today. We're going to go fast through many topics. So I'm going to talk for half an hour about the general description of SOFIA and of Cycle 9. And then there will be 5 examples that are more hands-on on how to calculate signal to noise and observing time and prepare astronomical observing request for each instrument. And there we'll have some extra time for Q&A, but of course questions are welcome at any time. So now I'm going to start sharing my presentation. Here it is. I'm going to put it in full screen mode. Can you hear me fine and see the screen fine? I assume yes.
Yes, we can.
That's great. Okay, so first, I just want to spend a couple of minutes talking about infrared astronomy, why you're familiar with it, but maybe you don't know if or why you would need it. Well, mostly the emission that you will see in the mid and far infrared is emission re-radiated from starlight that heats up dust and gas around it. So when you go to mid-infrared and far-infrared light, you're looking at things that are cold-ish. We're talking inner dust in protoplanetary disks, for example, or dust in the outer envelopes from stars, gas in star formation regions. This is the type of emission that you're looking at, and there's a lot of it. About half of the radiated energy in the universe is infrared. So the challenge here is that both infrared, mid and far infrared, I should say, is not observable from the ground. If you look here at this transmission plot, you have SOFIA transmission and SOFIA transmission on Atacama, one of the best sites in the world. You can clearly see that there are some areas where it's completely absorbed by the atmosphere. So SOFIA is this opportunity to have a platform at up to 45,000 feet for infrared observations. And how do I, sorry. Okay, sorry, the switch slide doesn't work very well. So the type of transitions and type of light that you see could be thermal emission from dust or from surfaces that may contain some spectral signatures of paths or silicate, and also many gas lines, either fine structural lines and rotational lines. Of particular interest when you're doing gas spectroscopy are water rotational lines. There are also some H2 forbidden lines and ionized line from all of these species that can easily be ionized by background starlight. One line that is a typical target is C2 because it has a huge role in the thermal balance of interstellar medium. And from these gas line measurements, you can derive, of course, composition, but also kinematics if you have sufficient spectral resolution, and temperature. So there's a lot of information to gather from gas spectroscopy. And from dust spectroscopy, where you have these bands that are typical of PAS and silicates, so you get composition and grade size distribution, also morphology, and if you have a polarimeter, polarization fraction and orientation, which may be connected to magnetic fields, of course. So these are really the type of information and observation emission that you get from infrared and far infrared spectroscopy. So I think that covers a significant fraction of the type of light that you would be looking at. So now, if you think this type of light is interesting for science, well, you probably will need to observe with SOFIA. There aren't many facilities where there are some balloons, but SOFIA is really the one that covers most of that range. So now I want to go through a few considerations related to the telescope, the optics, the instruments that are important to keep in mind when you're writing your proposal. Well, first of all, SOFIA, yes, it's great. It's flying high, but it's not a satellite. So there's still a bit of atmosphere up there, and it matters. I can hear me twice. Is that normal? Okay. So for example, here comparing Mauna Kea transmission and SOFIA transmission, clearly, I mean, the water vapor is 1,000 times better on SOFIA, but there's this 1% remaining that is still significant. And sometimes you will have to think about exactly the wavelength that you want to look at and understand the trade-off between transmission on SOFIA and the instrument noise at that specific wavelength. And sometimes source velocity matters. Velocity may be sufficient to put a line outside from a transmission window or inside it. So yes, it's high, but transmission still matters, and that's still something to think about when you're writing your proposal. Other consideration, it's a telescope that flies, so it moves, but the mirror inside doesn't move all around. It has some range of elevation that it can target. And this really much determines how the flight plans are built. So the maximum leg length, which is really a direction of the plane, is about 4 hours. And it's really easier to have observation being choppable in chunks of a few hours. So observation like long monitorings are especially challenging, so need to be very extra justified, which doesn't mean that your science isn't interesting, but it could be difficult to accommodate. And also consider that the plane also needs to return to base at the end of a flight each night. So this is an example of what a flight plan might look like. So it has this star shape and then returns to Palmdale. And these considerations make it that there is this special situation that the plane goes one way to see many targets that are asked, usually in the galactic plane and the ecliptic, and then returns and see the opposite direction. So there is the more there is demand on the galactic plane, the more available time there are on what we call inverse targets, so directions opposites. And we have published on our website, you can see this inverse target map, which lists zones of the sky where we tend to have more time available. So whenever you're doing something that is more of a survey, especially if it were to be extragalactic, you may have chance to get more time if you distribute your source around the sky and around high latitudes. So this is a tip really related to flight planning. Now, if I go to considerations on optics, the mirror SOFIA is 2.7 meters, and it is located in this zone of the plane where the pressure is lower and the temperature is very low, is maintained to be very low. And on the other side of this pressure bulkhead, you have the science instrument. So in practice, it looks like this. I am not able to recognize like this which instrument are attached, but these sticking things are the science instruments. 2.7 meter, that's big, but it's not gigantic. And considering it is on a plane and there is jitter, there is movement, well, the images are only diffraction limited above 35 microns. Lower than that, well, for example, at a very shorter wavelength, you tend to go around 3.5 arc second, PSF, and that's really from the pointing jitter. And this is after stabilization is applied, and stabilization works really well. I mean, this is an example on, I mean, it's done extremely frequently on a almost once per second. And this is an example on how the PSF looks when stabilization is applied and when it's not. So this gives you an idea of the type of spatial resolution that you would get at different wavelengths. And I would like to say a word about one of the main challenges of mid-infrared and far-infrared observations, not from satellite, is that infrared observations are completely background dominated. And that's the main challenge, and that can be addressed both by observing strategies and by data reduction strategies. And not only it's bright, but it varies very quickly. So you have a couple of ways to address that. There are, the observation must have a reference on the sky. It could be done either with chopping and nodding, but also on the fly observations where the telescope is moving during the observation. And each instrument will have a few modes to subtract sky better. And there will be more discussion about that when the different examples are presented. So typically, whether do you want to have a symmetric chop mode or an asymmetric chop mode, depending on how the background looks. So this is a plot that I will show several times in the talks. That's the instrument suite. We have 6 science instruments at the moment: FPI Plus, Axis, Forecast, FIFI-LS, Hawk Plus, and Great. And here you see them compared to Webb and ALMA bands. So really, SOFIA covers most of this mid and far infrared spectrum at a variety of spectral resolution. You have imaging instruments like Forecast and Hawk, and very high spectral resolution from Axis and Great. And you have to understand that these instruments can be swapped, but it takes time, and you can certainly not swap overnight. Actually, overnight is possible, but not during a flight. So the strategy here is that instruments are installed, and then a series of flights using that instrument are scheduled. And that the series of flight is called the series, observation series. And yeah, they can be several weeks long. And so typically during a cycle, you would have the same instrument coming up once or twice only. So that again, think about how that may impact monitoring observation, for example. The scheduling can be a little complicated, and when and how long this series happened, that's really made based on the proposal pressure. So what people with high priority proposal of very interesting science have asked for. So I'm going to go through those 6 instruments quite quickly. For first of all, Forecast, that's our mid-infrared imager, and it does have rhythm. So you can do imaging and low resolution spectroscopy, quite a big array, 256 pixels on each side. And this instrument is really good for dust low resolution spectroscopy, some atomic and ionized features, and also it's comparable to some Spitzer instruments, but it does not saturate on bright sources. So important project that has been done recently is a survey of the galactic center that complements Spitzer observation because it does not saturate on those very bright regions. So here is the list of prism and filter details, but I'm not going to go in detail into it. I recommend looking at the Observer's Handbook that has a chapter on each instrument with the specific details. Our X's is our mid-infrared high-resolution spectrometer. That's Echelon cross-echelon instrument from 4.5 to 28.3. So that's really the pendant of Texas on the IRTF, but that observes those windows that cannot be gotten from the ground, from Mauna Kea. Very high spectral resolution, up to 100,000, really good for spectral survey of some bright sources like hot cores. If you can check out this Orino hot core line survey from the scene rank 1, for example, that can give you an idea of the type of data that you would be getting. Hot plus, now we're going to far infrared imager and polarimeter. So this would be similar to, I think, Spire aboard Herschel, but with the polarimetry capability. You have 5 bands going from 53 to 220 microns, an array that is 64 by 40, and half that if you want to go to polarization mode. It's diffraction limited at all bands because this is beyond 35 microns, and the work here is really dust polarization, dust distribution on galactic sources or AGNs or variety of sources. Then we go to FIFILS, that's our far infrared integral field spectrometer. So going from 50 to 200 microns, and you get a data cube. So the resolution can go up to 2000. This has been heavily used for fine structure lines, either galactic or extragalactic, so O1C2. GREAT is one of, I think, the most used instruments. That's terahertz heterodyne spectroscopy. It offers 6 bands with very high spectral resolution, so you can really resolve those line profiles. You have 2 bands that have these 7 beams array in 2 polarizations, and other ones have only 1 pixel. So this one would be more similar to Hi-Fi, but although it has a very similar sensitivity, it has faster mapping because it can provide the array, and it can map pretty large area in the interstellar medium, star forming region. These are typically the region that this instrument observe, although you can find other applications. And I will finish with the FPI Plus, this presentation of instruments. That's an instrument that is always mounted because it's the guider, but it can be used for some fast optical photometry. We have done occultation with it. So this is much shorter wavelengths, 330 and 1100 nanometers. Okay, so now I've gone through a very quick presentation of things you may need to have in mind on the fact that this is a moving telescope, 2.7 meters, with some jitter that is corrected, and 6 instruments on board, 5 of them being swappable. So now some tips on how to prepare your SOFIA proposal going from the science case to submitting. Deadline September 4th, so it's really coming up. I recommend that you have with you when you're preparing your proposal these different materials: the call for proposal on the website, observer handbook, the site website, which is our site time estimation tool, USpot, which is a tool to download that you will define, which you will use to define your observation and submit. And if you're missing any information, we have a help desk, and usually it's me on the other side. So feel free to shoot me any question or inquiry.
10 minutes.
Thank you. I won't go much into detail with science case. You probably are the best people to know your own science case, but there are a few pointers that I got from the call for proposal, a few things that are important and that we especially value at the project. So of course, main consideration is we want science that demonstrates significant scientific impact, but also we encourage programs that foster synergies from ALMA, HST, Spitzer. We place particular value on observation that may support future web observation, especially ERS observations. I think we have up to 20 hours reserved for programs that would be helpful for ERS teams. This year we have a Green Bank Observatory Joint Proposal Agreement, so also check for synergies with GBT, and survey proposals encouraged. We may set aside a significant chunk of time for survey proposal. There is also this criterion that is to evaluate the proposal, that is the degree to which the investigation use SOFIA's unique capabilities. So what is offered in this cycle, in short, you have this cycle of observation that is a bit over a year, that offers all 6 instruments. 3 instruments will have a sudden deployment. Great and Hawk during the summers of 2021 and 2022, and Fifi LS will have a shorter deployment in March 2022. We have a few new technical offerings, some standard modes, some shared risk modes as well, and an upgrade on grade that allows different polarization to be tuned to a different frequency. So your observation must fit in one of those 2 large categories: regular, which are for which we have up to 500 hours, and that includes surveys and target of opportunities, and legacy. Those are very large proposals, which have no proprietary period and to which the team commits to offer enhanced products. So a large chunk of time is reserved for those type of projects. We will have in cycle 9 up to 400 hours for legacy programs. So now that if you think mid-infrared is what you want, and it could fit in what SOFIA, your program could fit in what SOFIA offers, here are a few pointers on feasibility. So this plot that you already saw will give you the information on wavelength coverage, spectral resolution, and spatial resolution. Does your project meet those 3 parameters that SOFIA can offer? So does it cover the right spectral line that you want with the right spectral resolution that you need, for example, for kinematic studies? And does it resolve your source with the accuracy that you need? Once you have this idea, you can go a little more in depth and check whether the source has already been observed. Because first of all, there is a list of reserved observations that some science team have for GREAT and FIFI-LS. So you can check those on our website. And there are some reserved sources, but also if the source has already been observed, you will have to justify pretty thoroughly why do you want more sensitivity or more spectral resolution or something a little different that would justify re-observing. So check the SOFIA archive that is all at URSA. You will need then to find the expected signal of the source, and that's difficult, or that can be challenging. So you can get that from archival data, from your own models, but we will check that at the technical review stage. So please be thorough on that and careful, especially flux density or surface brightness, how you define your expected source signal may vary depending on the instrument. And now you have to define your desired SNR and link it explicitly to your measurable. Why do you want an SNR of just 5? Is it enough to get the science you want? Or why do you want an SNR of 100? Isn't that overkill? And once you have this estimate of SNR and wavelength that you need and expected flux, then you can get to site and you will have output that is an integration time. So I'm going to go very quickly through the last steps. A few pointers. This is an estimation time per on point or on off pair. So if you're doing a map, you will have to multiply to the number of pointings. And it's also a needed time per array element. So it doesn't include calibration overheads. Those will be calculated by the USPOT tool. And then you can compare your request to the typical request that we have in a different cycle. So these are the time requests in cycle 8. You can launch USpot after downloaded it. Very simple. You have a cover page, define target section, and then define AORs, which is the part that the different example will go in detail. Then you will have to build the justification PDF. So that's the most important point probably. And starting this cycle, we're following dual anonymous guidelines, which means that this justification must be anonymized. So the tag doesn't know your identity at the moment of science review, and hopefully that helps to make the review more about science. So anonymized, we have a lot of details in our website, and we even recorded a webinar about that. But yeah, don't actively identify yourself. But I think there was a quote at some point that was, you're not trying to hide, but just not show you who you are. But we're taking it seriously. If there's blatant disregard, that may lead to proposal rejection. So please do not hesitate to send us any question you may have about how to make it compliant. And this is a post-deadline timeline. Observations would happen starting July 2021. And the data after observation is processed and staged in the URSA archive. And then we can still help you after delivery with assistance about data analysis. Again, help desk, but also we have some recipes on how to get you started with your data that you can start looking at yourself. And I'm done. This is just a summary of the funding opportunities that we have for US-based GOs. I can go back to this. And yeah, question to the help desk. And if you aren't signed up to the newsletter, I really recommend it. This is QR code. I'm done for now. Any questions?
I do see one question. There's 2 questions in the chat.
I see. Is there a batch mode for site? Is there a batch mode for site? Yes, I've seen, but not for everything. For some AORs, can someone help me here? Is that definitely to upload targets? There are ways to do that. You can upload a file of targets, and for AORs, then there are ways to assign to your list of targets the same AOR, so you don't have to redefine for each target the same or similar AOR. Is that what the question was about? I'm not completely sure. For FIFI-LS or for other instruments? For different Z's for FIFI-LS. Oh, I'm going to ask to Robert. Robert, can you?
I don't think there is a batch mode for that. I don't believe so. I have the site window open, of course, because I'm about to use it in my talk. No, I think you just upload the source velocity. We don't have a batch mode implemented at this moment. That is something we could think about doing if there are like to be lots of sources in at different redshifts. surveys?
Yeah, I guess we never really ran into it because extragalactic sources with Fifi, I haven't seen a survey that spans so much that you would have to.
You normally do look at all the sources, though.
Okay. Okay, well, we'll see how many sources you have and deal with it. And we have a question from Kevin Cook. How oversubscribed are regular versus regular survey versus legacy? The only number I know of is oversubscription of number of hours of regular, and that's 5. I do not know about the survey and the legacy, but Jim Jackson is online and he's responding to this.
Yeah, so the legacies are slightly more oversubscribed. It's about a factor of 6 in terms of hours requested to hours available. Surveys, we don't really keep track of them as a separate category, but I would imagine the oversubscription rate is similar to the GEO programs.
Thanks, Jim.